Bismillahirrahmanirrahim. Chapter 2, Structure of Atoms. Introduction. Ancient Greek philosopher Democritus Democritus suggested that matter is composed of tiny invisible particles called atoms. The name atoms was derived from the Latin word atoms, meaning invisible. In the beginning of 19th century, Dalton put forward atomic theory. According to it all matter is made up of very small invisible particles called atoms. That atom cannot be subdivided. However, in the beginning of 20th century, experiment performed by Goldstein, J.G. Thomson, Rutherford, Bohr, and other scientists revealed that atom is made up of some atomic particles like electron, proton, and neutron. Properties of these subatomic particles will be discussed in this chapter. Theories and experiments related to structure of atoms. According to Dalton, an atom is an invisible hard dense sphere. Atoms of the same element are compound are alike. They combine in different ways to form compound in the light of Dalton atomic theory. Scientists performed a series of experiments, but till late 19th century, scientists discovered new subatomic particles. In 1886, Goldstein discovered positively charged particles are called protein. In 1897, J.J. Thomson found in an atom the negatively charged particles known as electron. It was established that electron and proton are fundamental particles of matter. Based upon these observations, Thomson put forth his Coulomb pudding theory. He postulated that atoms were solid structures of positively charged with tiny negative particles stuck inside. It is like plum in the pudding. Cathode rays and discovery of electron. In 1870, in 1895, Sir William Crookes performed experiments by passing electric current through gases in a discharge tube at very low pressure. He took a glass tube fitted with two metallic electrodes which were connected to a high voltage battery. The pressure inside the tube was kept 10-4 A atom. When high voltage current was passed through the gas, shiny rays were emitted from the cathode which traveled towards that anode as shown in figure. These rays were given the name of cathode rays that these were emitted from the cathode. The cathode rays were studied in detail and their properties were determined, which are given below. These rays travel in a straight line perpendicular to the cathode surface. They can cast a sharp shadow of an opaque object. If placed in their path, they are deflected towards positive plate in an electric field, showing that they are negatively charged. They rise the temperature of the body on which they fall. J.J. Thomson discovered their charge mass EM ratio. Light is produced when these rays hit the walls of the discharge tube. It was found that the same type of stars were emitted to no matter which gas and which cathode was used in the discharge tube. All these properties suggested that the nature of cathode rays is independent of the nature of the gas present in the discharge tube or material of the cathode. The fact that they cast the shadow of an opaque object suggested that these are not rare, but they are fast-moving material particles. They were given the name electrons since all the material produce same type of particles. It means it means all the materials contain electron, as we know material are composed of atoms, hence the electron are fundamental particles of atoms. Discovery of proton in 1886, Goldstein observed that in addition to cathode rays, other rays were imitated, also were rays present in the discharge Discharge tube. These rays were traveling in opposite direction to cathode rays. He used a discharge tube having perforated cathode as shown in figure. He found that these rays were passed through holes in present hole present in the cathode and produce a glow on the walls of the discharge tube. He called these rays are canal rays. The properties of these rays were following. These rays travel in straight line in a direction opposite to cathode rays. Their deflection in electric and magnetic field provide that these are positively charged. The nature of canal rays depend upon the nature of gas present in the discharge tube. These rays do not originate from the anode. In fact, these rays are produced when the cathode rays or electrons collide with the residual gas molecules present in the discharge tube and ionize them as follows. Mass of these particles was found equal to that of proton or simple multiply of it. The mass of a proton is 1.4940 times more than that of an electron. Thus, these rays are made up of positively charged particles. The mass and charge of these particles depend upon the nature of the gas in the discharge tube. Hence, different gases produce different type of positive rays having particles of different masses and different charges. Keep in mind that positive particles produced by a gas will be of the same type. Positive rays produced by the lightest lightest gas, hydrogen as proton. Discovery of neutron. Rutherford observed the atomic masses of the element could not be explained on the basis of the masses of electron and proton only. He predicted in 1920 that some neutral particle having mass equal to that of proton must be present in an atom. The scientists were in search of such a neutral particle. Eventually, in 1932, Chadwick discovered neutron when he bombarded alpha particles on a beryllium target. He observed that highly penetrating radiations were produced. These radiations were called neutrons. Properties of neutron are as follows. Neutrons carry on charge. They are neutral. They are highly penetrating. Mass of these particles are nearly equal to the mass of a proton. Rutherford atomic model. Rutherford performed gold foil experiment to understand how negative and positive charge could coexist in an atom. He bombarded alpha particles on a 0.0004 centimeter thick gold foil. Alpha particles are emitted by radioactivity elements like radium and polonium. These are actually helium nuclei He2, plus they can penetrate through metal. He to some extent he observed the effect of a particle on a photographic plate on a screen coated with zinc sulfate. Zinc sulfide as shown in figure. He provided the Plum coding model of the atoms was not correct. Observations made by Rutherford were as follows. Almost all the particles passed through the foil and reflected out of 20,000 particles. Only a few were deflected at fairly large angles and very few bounced back on hitting the goal. Result of the experiment. Keeping in view the experiment, Rutherford proposed planetary model for an atom and concluded that following result. Since most of the particles pass through the foil deflected undeflected, therefore most of the volume occupied by an atom is empty. The deflection of a few particles Proved that there is a center of positive charge in an atom which is called nucleus of an atom. The complete boson of a few particles show that the size of that they show that the nucleus is very dense and hard. Since a few particles were deflected, show that the size of the nucleus is very small as compared to the total volume of an atom. The electrons revolve around the nucleus. An atom as a whole is neutral. Therefore, the number of electrons in an atom is equal to the number of protons. Expect electron. All other fundamental particles that lie within the nucleus are known as nucleons. Rutherford atomic model. Although Rutherford experiment provided that the plum pudding model of an atom was not correct, yet it had following defects. According to classical theory of radiation, electron being the charged particles should release or emit energy continuously, and they should ultimately fall into the nucleus. If the electrons emit energy continuously, they should form a continuous spectrum, but its fact line spectrum was observed, although the scientists have had objection on the atomic model present by Rutherford, yet it cultivated through provoking ideas. Among them, they initiated the quest of to answer the following question. Bohr atomic theory. Keeping in view the defects in Rutherford atomic model, is Bohr present and other model of atom in 1913, the quantum theory of Max Planck was used as foundation for this model. According to Bohr model, revolving electron in an atom does not absorb or emit energy continuously. The energy of a revolving electron is quantized as it revolves only in orbit of fixed energy called energy levels by him. The Bohr atomic model is shown as in figure. The Bohr atomic model was based upon the following postulates. The hydrogen atom consists of a tiny nucleus and electrons are revolving in one of circular orbit of radius r around the nucleus. Each orbit has a fixed energy that is quantized as long as electron remains in a particular orbit. It does not radiate or absorb energy. The energy is emitted or absorbed only when an electron jumps from one orbit to another. When an electron jumps from lower orbit to higher orbit, it absorbs energy, and when it jumps from higher orbit to lower orbit, it radiates energy. This change in energy delta I is given by following Planck equation. Delta E is equal E2 minus E1 is equal HV, where H is Planck constant equal to 6.630 multiplied 10 to the power minus 24 JS, and V is frequency of light. Electrons can revolve only in orbit of a fixed angular momentum. NVR given as NVR is equal NH divided by 2 pi, where N is the quantum number of orbit number having values 1, 2, and 3, and so on. Quantum means fixed energy. It is the smallest amount of energy that can be emitted or absorbed as electromagnetic radiation. Quanta is plural of quantum. In 1918, Nobel Prize in Physics was awarded to German physician to Max Planck 1850 minus the 1947 for his work on the quantum theory. Summary of difference between two theories. Rutherford atomic theory, Bohr atomic theory. Rutherford atomic theory, it was based upon classical theory. Bohr, it was based upon quantum theory. Rutherford, electrons revolve around the nucleus. Bohr, electrons revolve around the nucleus in orbit to fixed position. Rutherford, no idea about orbit was introduced. Orbit had angular momentum. Bohr, rather, atoms should produce continuous spectrum. Bohr, atoms should produce the spectrum. Rutherford, atoms should collapse. Bohr, atoms should exist. Electronic configuration. Before discussing electronic configuration, let us first understand the concept of shell and subshell. We have learned about the structure of atoms. It consists of a tiny nucleus lying in the center and electrons revolving around the nucleus. Now we will discuss how the electrons revolve around the nucleus. The electrons revolve around the nucleus in different energy levels or shells according to their respective energies. Potential energy. The concept of potential energy of an electron shall be discussed in higher classes. Energy levels are represented by n values 1, 2, 3, and so on. They are designated by the alphabets K, L, M, and so on. A shell closer to the nucleus is of minimum energy. Since K shell is closest to the nucleus, the energy of shells increase from K shell onwards, such as N shell can accommodate पेज नंबर 35 मिस है वो मैं बुक से रीड कर देती हूँ. First energy level is K shell. It has the lowest energy. Second energy level is K L shell. It has more energy than K shells. Third energy level is M shell. It has more energy than K and L shells. Fourth energy level is N shell. It has more energy than K, L, and M shells. In simple words, shells are the main energy levels that electrons can occupy. Shells are represented by circles around the nucleus. They are counted from the center outward as shown in figure. The number of electrons that a shell can accommodate is given by 2 and 2, where n is the shell number. A shell also consists of subshell. The number of subshell in a shell is equal to its value. Each subshell is designated by a simple alphabetic particle S, P, D, F, etc. First energy level or K shell has only one subshell called as subshell. Second energy level or L shell has two subshell S and P. Third energy level M shell has three subshell S, P, and D. Fourth energy level or N shell has four subshell S, P, D, and F. Electronic configuration of a certain element. The distribution of electron around the nucleus in various shell and subshell according to that increasing energy is called electronic configuration. The most stable or ground state electronic configuration of an atom is the one in which electrons are present in the lowest possible energy level. The electrons fill the shells in order of their increasing energy. Lower energy level is occupied first, then the higher energy level, and so on. As indicated earlier, the maximum capacity of shells to accommodate the electron is as following. K shell can accommodate 2 electrons, L shell can accommodate 8 electrons, M shell can accommodate 18 electrons. N shell can accommodate 32 electrons. As we know, there is a slight difference between the energies of the subshells within a shell. Therefore, filling of electron in subshell of a shell is such as that B subshell is filled first and then its B subshell and then other subshell are filled. The maximum capacity of subshell to accommodate electron is S subshell can accommodate 2 electron, P subshell can accommodate 6 electron. Let us write the electronic configuration of the element and their ions one with the help of a few examples. Keep in mind we should know three things: the number of electrons in an atom, the sequence of shells and subshells according to the energy level, the maximum number of electrons that can be placed in different subshell and shells. The electronic configuration of first 18 elements, the sequence of filling of electrons in different subshells it as follows: 1s2, 2s2, p2, p6, 3s2, 3p6. One number represents the shell number while letters S and P represent subshell. The superscript show the number of electrons in a subshell. The sum of superscript number is the total number of electrons in an atom. Atomic number of an element. The electronic configuration of a certain element is shown in the table 2.1. Isotopes. Definition: isotope are defined as the atom of an element that have same atomic number but different mass number. They have same electronic configuration and number of proton, but they differ in the number of neutrons. Isotopes have similar chemical properties because these depend upon electronic configuration, but they have different physical properties because these depend upon mass number. Most of the elements have isotope. Here we will discuss the isotope of hydrogen, carbon, chlorine, and uranium. Only examples: isotope of hydrogen, the neutrally occurring hydrogen is combination of three isotopes present in different abundance. These three isotopes of hydrogen are named as protium, deuterium, and tritium. Each one of them has one proton and one electron, but number of neutrons are different in mass. Different as shown in table. Isotope of carbon. There are two stable isotope of carbon and one radioactivity isotope. The isotope is represent the abundance of 98.9%, while 13C and 14C are both present only 1.1% in nature. All of them have the same number of proton and electron but differ in number of neutron. They are represented as follows. Isotope of chlorine. There are two isotopes of chlorine. There are two isotopes of chlorine. Isotope of uranium. There are three isotopes of uranium is found in nature. Nearly 99%. The difference in their number of electron, proton, and neutron of the neutron is shown as table below. Uses applications of isotope. Application of isotopes in science and many different technologies. Field isotope have vast application. The biggest by application is in the field of medicine. They are applied in diagnosis, radiotherapy, and treatment of many diseases like cancer. Uses with the advancement of the scientific knowledge, the isotope have found many applications in our lives. Following are the major fields in which isotope have the vast applications. Radiotherapy, treatment of cancer. For the treatment of skin cancer, isotopes like P32 and SR19 are used because they emit less penetrating beta radiation. For cancer. CO60 affecting with the body is used because it emits strongly penetrating gamma rays. Trace for diagnosis and medicine. The radioactivity isotope are used as tracer in medicine to diagnose the presence of tumor in the human body. Isotope of iodine 131 are used for diagnosis of goiter in the thyroid gland. Similarly, technetium is used to monitor the bone growth. Radiological and geological uses. The radioactivity isotopes are used to estimate the age of fossils like dead plants and animals and stones, etc. The age determination of very old base object based on the half lives of the radioactivity isotope is called radioactivity isotope dating, an important method of age determination of old carbon containing object fossil by measuring the radioactivity of C14 in them is called radiocarbon dating in simple carbon dating. Chemical reaction and structure determination. The radioisotope are used in a chemical reaction to follow a radioactive element during the reaction and ultimately to determine the structure. For example, C14 is used to label CO2 as CO2 is used by the plant for photosynthesis to form glucose. Its movement is detected through the various intermediate steps up to the glucose. Application in power generation. Radioactive isotopes are used to generate electricity by carrying out controlled nuclear fission reactions in nuclear reactor. For example, when uranium-235 is bombarded with slow-moving neutrons with uranium nucleus breaks up to produce barium-139 and krypton-94 and 3 neutrons. A large amount of energy is released, which is used to convert water into steam in boilers. The steam then derives the turbines to generate electricity. This is the peaceful use of atomic energy for development of a nation.